Hello, everyone, and welcome back to Rahna Model. I'm so excited to have you here today. We are going to dive deep into something that is absolutely essential for your coding interviews: data structures. Whether you are just starting your coding journey or you are already preparing for those big companies' interviews, mastering data structures is going to give you that competitive edge you need. In this video, we'll walk through 15 data structures together, everything from beginner-friendly concepts all the way to advanced topics. And the best part, I have prepared some code for you in Python for each one of the data structures with clear and practical examples. By the end of this video, you'll have a solid foundation that will make a real difference in your interviews. Let's get started. Let me share something important with you. Data structures aren't just theoretical concepts you learn in a school. They are the backbone of efficient and scalable code. And that's exactly what interviewers are looking for. When you are in an interview, they are not testing if you can write code that works. They want to see if you can write code that works efficiently. Choosing the right data structure can make the difference between big OM solution that passes all test cases and big OM2 the solution that times out. So here's what I want you to focus on. Practice consistently, even just 30 minutes a day. Understand why a data structure works, not just how. Always think about time, space complexity before coding. Learn from each mistakes. They're stepping stones to success. So the interview preparation journey can feel overwhelming, but you are doing the right thing by being here. Every concept you master brings you one step closer to your dream job. Let's tackle this together. Uh, Now let's start with the foundational building blocks. These 8 beginner level data structures are the ones you will encounter most frequently in both interviews and real world programming. These structures form the basis for everything we'll cover later. So it's really important to get comfortable with them. Think of them as your toolkit. Each one designed for specific types of problems. So here's what we'll cover. Linked lists, perfect when you need dynamic in memory management. Circular linked list, great for round robin type scenarios. And doubly linked lists, when you need to move both forward and backward. Circular doubly linked list, the same as circular linked list, but combining the best of both worlds. And queues, ideal for first come, first serve situations. And priority queues when some tasks matter more than the others. Stacks, excellent for LIFO scenarios like undo functionality. And hash tables, your go-to for lightning fast looks up. And don't worry if any of these sound unfamiliar right now. And we are going to break down each one and understand how it works, implement. I show you the code in Python. You can practice by yourself and see when to use it. And by the end, these will feel like old friends. Let's begin with one of the most fundamental data structures, the linked list. I want you to think of it like a treasure hunt, where each clue points you to the next one. A linked list is a linear structure where each element, which we call a node, contains two things: the actual data and the pointer, or a reference to the next node. This is different from arrays. where all elements sit next to each other in memory. Why is this useful? Well, arrays have a fixed size and need contiguous memory. Linked lists, on the other hand, can grow dynamically. You can add or remove nodes anytime without worrying about memory allocation. Let's look at the code. Here we have a class node, which has a data, and next, which is a reference to the next node. And another class is linked list. It has several methods. One of them is insert, delete, and traverse. So insert add a new node to the end, and delete remove a specific node. Traverse visit each node in order. Let's look at the performance here. As you can see, all of them, insert, delete, search, have a big O-M complexity. Insert, we walk through the list to find the end. Delete, we need to find the node first. And search, we might need to check every node. So yeah, and linked lists are everywhere. Think about your browser's undo feature. Each action is a node. You can step back through, or music playlists where you can go from one sign to the next. Even your file system uses linked list concepts. Common questions you might see include reversing a linked list, detecting cycles, or finding middle node. Practice these and they come up often. Now let's look at an interesting variation of the circular linked list. As the name suggests, it is like taking a regular linked list and connecting the last nodes back to the first, creating a continuous loop. In a normal linked list, the last node points to none, signaling the end. But in a circular linked list, the final node points back to the head. This means you can start from anywhere and traverse infinitely in a circle. Where would you use this? Imagine you are building a round-robin scheduler for CPU process. The processors cycle through processes over and over. A circular linked list models this perfectly. You keep going through the list repeatedly. So let's look at the code. As you can see, most of them are the same as before. We have class node, class circular linked list. It has insert and traverse here. And here, as you can see in insert, if current current equals self head, if when we are back at the head. That's the difference. And look at the performance. Insert, search, and delete as the same. They have big OM complexity. And one thing to be careful about, infinite loops. When you are writing traversal code, you need to check if you have returned to your starting point or you are a loop forever. So as I said, use cases like round-robin scheduling systems, audio-video streaming buffers, and implementing game loop where players take turns. Questions often ask you to detect if a linked list is circular or find the start of a cycle. These are classic problems that test your understanding of pointer manipulation. Here's where things get really interesting. A doubly linked list has a powerful feature. You can traverse in both directions. Remember how a regular linked list only has a next pointer? Well, in a doubly linked list, each node has two pointers, one pointing forward to the next node and one pointing backward to the previous node. Think of it like this. In a regular linked list, if you are at node C and want to go back to node B, you can't. You would have to start all over from the beginning. But with a doubly linked list, you have a direct path backward too. So if you look at the code, you can see in class node there are two different pointers, one next and one for previous. And there are some methods, insert, connect new node, both forward and backward. Delete can efficiently remove a node if we have its reference. Traverse forward, go from head to tail, traverse backward, go from tail to head. For performance, it is the same. All of them have big O, N, and doubly linked lists give you bidirectional power, but they come at a cost. Each node needs extra memory for the backward pointer and the implementation is more complex. But in many cases, this trade-off is absolutely worth it. And for real world applications, I can say browser history, go back and forward, music player controls, text editors, and undo redo with the full history of the navigation. So if you can implement a double linked list confidently, you are showing you understand pointers at a deeper level. Questions often test deletion given only a reference to the node, which is big O1 in double linked lists. This is our most complex linked list variant, the circular double linked list. It combines the bidirectional power of double linked lists with the infinite traversal capability of circular lists. In this structure, every node has both a next and previous pointer, and the last node's next connects back to the first, while the first node's previous connects back to the last. It's a complete loop where you can go forward or back for indefinitely. So why would you use something this complex? Honestly, I don't know. In most production code, you probably won't, but in interview settings and a specific application like navigation system or I think game menus, this structure can model real-world scenarios perfectly. If you look at the code, there are previous and next, and uh, the last one in the insert, you can see it connects to the head. And for performance, as you can see, it is the same as before. But this structure requires you to manage four connections with every insertion. Next and previous for the new node and node it's connecting to. It's complex, but mastering this shows you truly understand pointer manipulation. So for use cases, as I said, maybe navigation systems that loop indefinitely, or a game asset management, or certain cache implementation. But you likely won't see this in many real interviews. But knowing it exists and understanding its implementation demonstrates your depth of knowledge. It's those extra details that can set you apart. Now let's move forward from linked list to data structure you encounter in everyday life all the time, the queue. A queue follows the FIFO principle, first in, first out. Think about the last time you stood in the line of the grocery store. The first person in line gets served first, and new people join at the back. That's exactly how a queue works in computer science. So if you look at the code, it has a class queue. It has some methods, enqueue, dequeue, pick, which enqueue shows add an item to the back of the queue, and dequeue remove the item from the front. Pick looks at the front item without removing it. So as you can hear, we used dequeue from collections because of its efficiency. And but why dequeue and not list? That's a great question. Python list has a big on time for removing from the front because all elements need to shift. But dequeue gives us just big O1 for both append and pop left. Always remember, use the right tool for the job. That's important. So for performance, as you can see, enqueue, dequeue, and pick, all of them have big O1. But for real world scenario, I can say printer job queue, documents print in order received, or CPU scheduling, processing run in order of arrival, or customer service systems, customers served in arrival order. And another thing is that BFS, Best First Search in Graph, uses queues. It's a good point to remember. And queue questions often test your ability to implement using arrays or stacks or reverse queue. This tests your understanding of the FIFO principle and your creativity in problem solving. So what if not all elements deserve the same priority? That's exactly where priority queues come into play. They are like regular queues, but with a twist. The most important item gets served first, regardless of when it arrived. Think of it this way. In a hospital emergency room, a patient with a heart attack needs the treatment before someone with a broken arm, even if the broken arm patient arrived earlier. A priority queue modeled this perfectly. So how it works internally. Priority queues typically use a heap data structure, which we'll cover separately. For now, just understand that elements are stored in a way that lets us quickly find and remove the highest priority item. So if you look at the code, we used the heap queue here, and as you can see, it has some methods like push, pop, or pick. So by default, heap queue implements a min heap, meaning smaller numbers have higher priority. If you need the opposite behavior, you can negate the prior priority value. It's a common pattern, and it's so useful. So for the performance, as you can see, for insert and delete, it has a big O log n, and for pick, it just has a big O1. For real-world applications, I can say operating system task scheduling, real-time tasks get a priority, network routing, critical data packets first, and digester are shortest path algorithms, always process closest ones. And stock trading, high-value trades prioritize. So one of the most common priority queue interview question is to find the k element, k largest element. It's a perfect example of when a priority queue shines over sorting. So let's talk about one of my favorite data structures, the stack. It follows the LIFO principle, last in, first out. The classic analogy is a stack of plates. When you add a plate, you put it on top. Then you remove one, you take from the top. You can't easily remove the bottom plate without removing everything above it first. So in programming, as you can see, uh, the class stack has some methods: push, pop, pick. Push add an item to the top of the stack. Pop remove the top item, and pick just look at the top item without removing it. And its implementation is so simple, as you can see. It has nothing so special. And why list works perfectly here? As you can see, in a stack, you have self-stack as a list. Python's list has big O1 append and pop at the end. That's exactly what we need for a stack. Remember earlier I mentioned not using list for queues. For a stack, list is perfect. So don't forget it. And performance for push, pop, pick for all of them, big O1. Nothing special. And for real world applications, expression evaluation, compiler uses a stack for parsing. The function called the stack. When you call the function, it's pushed. When it returns, it's pop. And there is a classic problem here, bracket matching. And one of the most common stack interview questions. Given a string of brackets, determine if they are imbalanced. Each opening bracket gets pushed. Each closing bracket must match the top of the stack. It beautifully demonstrates a stack power. Now we are getting to one of the most powerful data structures in your toolkit, the hash table. This is what makes Python dictionaries and JavaScript objects work their magic. A hash table gives you big O1 average case time for lookups. Think about that. You can find a value almost instantly, no matter how much data you have. That's incredible. How does it work? The magic happens through hash functions. When you store a key value pair, the hash function converts the key into an index in an array. When you want to retrieve the value, the hash functions takes you directly to that index. So as you can see in the code, the class hash table has the size, self.size, and self.table. It has some methods, hash insert, and you can look at it by yourself, and you can practice by yourself. And there's something important here. It's called handling collisions. Sometimes two different keys hash to the same index. It is called the collisions. We handle it with chaining, storing multiple items at the same index in a list. That's why we have a list of lists here. If you look at that for table. For performance, for big O1, in average case for insert, delete, search. In worst case, I can say it's rare. Big O N if everything collides. Yeah, that's unfortunate. So in real world importance, oh yeah, yeah, there is a good example: database indexing. This is how database finds records so fast. Caching systems, Redis, if you worked with it, Redis use hash tables. And symbol tables in compilers, tracking variable names and values, and your Python dictionaries every day. So hash tables have something called a load factor. That's I just learned here. No, I'm kidding. The ratio of elements to table size. When this gets too high, typically above 75%, I think, we resize and rehash everything. This keeps our big O1 performance. So hash tables are interview favorites. Questions often ask you to implement FAANG from scratch, handle collisions, or use hash tables creatively to solve problems like finding pairs that sum to a target value. And key hash is so useful if you have a big table and you don't want to, I don't know, find a pass between two elements. You just created the table of the all the paths with hash tables.